Welcome to Technologyverse.
If you use the timeline scrubber to skip ahead 10 seconds in this video, you're interacting with a stream of high-density data that moves so fast it's effectively instantaneous. To someone living in the mid-1800s, this would look like literal magic. For most of history, human communication was trapped by physical limits. A message could only move as fast as a horse could gallop, a ship could sail, or as far as the human eye could see. This is an early optical telegraph. By perching a mechanical semaphore signaling device atop a stone tower, operators could relay visual patterns from one horizon to the next, finally moving information faster than a physical courier. Overcoming this tyranny of distance, the delay inherent in physical travel, became the singular obsession of telecommunications. The breakthrough came in the 1830s with the electrical telegraph. It was the original digital system, using copper wire to translate complex language into a binary-like code of dots and dashes. But Morse code was slow and required a specialist to decode. In 1876, Alexander Graham Bell solved that bottleneck, inventing a telephone that could transmit the actual frequencies of the human voice. By the early 1900s, Guglielmo Marconi removed the wires entirely. His commercialization of wireless radio allowed ships and stations to communicate across open oceans using electromagnetic waves. But these early systems shared a fatal flaw. They relied on continuous analog waves. Because analog signals are continuous, they rapidly degrade over long distances and pick up interference from the world around them. An analog network can only carry so many signals before the airwaves or wires are physically full. As long as communication stayed analog, an instantaneous global network for billions of people was a physical impossibility. The shift into the 1950s semiconductor era forced a realization. To build a truly global network, engineers had to stop sending waves and start sending math. Instead of a continuous wave, information was measured and broken down into a discrete stream of ones and zeros. This binary code allowed computers to reconstruct data with zero errors, regardless of the distance. Processing these digital signals originally required massive hardware, like the room-sized mainframe computers seen here. It took the invention of the transistor and CMOS technology to shrink these processors onto the tiny microchips we use today. Once data was digital, engineers could use packet switching. This method breaks a single file into tiny, independent chunks that can take different paths through a network, reassembling perfectly at the destination. This architecture created the internet. Because the data isn't tied to one single wire, it can flow around broken paths or congested nodes, ensuring the network survives even if individual parts fail. Digitizing and packing data unlocked the ability to scale. It rewrote the rules of distance and capacity, providing the technical platform for the mobile era. 1G arrived in the 1980s as the first real mobile voice network. It was a breakthrough, but because it was analog, the quality was poor. The phones were huge, and it had zero capacity for digital data. The 2G networks of the 1990s digitized the signal. This improved quality and shrank the hardware, but it also introduced a new feature, the ability to send tiny packets of data known as SMS text messages. The next bottleneck was speed. As this chart shows in the F3G column, 3G networks solved this by bringing high-speed mobile internet to pocket devices, enabling HD video and digital services. But as we used more data, we needed more bandwidth. 4G networks provided mobile broadband, which was fast enough to support 4K video streaming and the entire modern economy of mobile apps. Each generation multiplied the network's capacity, moving the phone away from its origins as a voice tool and into its role as a digital lifeline. 5G moves beyond the speed improvements of 4G, introducing an architecture designed to eliminate latency, the tiny delay between a signal being sent and a response being received. Near-zero latency solves the bottleneck of real-time response. It allows the network to act like a reflex, which is necessary for machines that have to make split-second life-or-death decisions. This enables the Internet of Things, where devices like autonomous vehicles can coordinate and traffic instantly without waiting for a human to intervene. Telecommunications has shifted its focus. We are no longer just connecting people. We are building a network to coordinate the autonomous physical world. This global connection relies on a massive physical infrastructure that we rarely see. It's an orbital web that began with the Telstar satellite and now includes millions of miles of undersea fiber optic cables. This vast network functions as a digital nervous system for the planet, allowing us to sense and react to data globally in an instant. The journey from a single copper telegraph wire to an omnipresent multi-gigabit network is one of the most significant engineering feats in our history. Our history shows that whenever we hit a physical limit, we find a way to engineer a path through it. The story of telecom proves that our drive to connect will continuously outsmart the limit.
If you really feel the video is helpful, click like, share, and subscribe button. Thank you for watching.